Hello, welcome again to the second part of this lecture on system modeling, week 8 of our software engineering course. Just to recap, last time I talked to you about the role of models and how models facilitate software development because they simplify certain complex aspects of the system. They make our assumptions more explicit, and the term explicit is really very, very important because once you put things down in a model, then other people can inspect and check the models. They read them with you and discover maybe omissions, mistakes, inconsistencies, and so on. Models are important to model requirements and analyze these requirements, make sure that they're valid, they're working, they are consistent, they are as complete as can be, they do not contradict the actual reality of the domain you're trying to model. That's at the requirement stage. Models are also important at the design stage because they help you plan your design, plot your design in advance of you writing any code or procure any equipment. Models are also very important to help you and your teammates as well as other stakeholders involved in the development to make decisions and make trade-offs. You need to discuss your designs, you need to discuss your options and alternatives with your clients and users, and putting these down on models make sure that you have a greater opportunity of eliminating misunderstanding and smoothing things out, and therefore be able to make better and more informed and valid decisions. So the role of models is really, really crucial. Now, I also mentioned something about the different perspectives or viewpoints from which you can model the same software system. So you can model the system from a contextual viewpoint, i.e. show the system within its context, what's surrounding it, maybe other systems, maybe types of organizations or people you need to respond to or interact with, that is your system. What sort of exchanges, what sort of hardware that needs to be around, or services, maybe something like the internet and stuff like that. So this is like a kind of contextual model you might want to show up in your software development activity early on. I also say something important about contextual models, which is they help you greatly in debating and determining the boundaries of your system. What is the scope of your system? What are the responsibilities that are included within the system that you're aiming to develop? We also mentioned process-oriented models to show how a particular process is performed. What are the elements of that process? What is the flow of activities within that process? What are the data flow and exchanging between elements of the process? So that will be a process-oriented view. Another view is the interaction point of view, maybe interaction with other systems, interaction with user, interactions between parts of the system itself, components, objects, classes, whatever. Obviously, complex system will have to have various parts to them, yeah? Not just one, multiple parts that are interacting together. So they have to send each other things and respond and stuff like that. So this would be an interaction type of model. I also mentioned the structural type of model, whereby we're describing what we can also term as the static structure. The structure that does not show what it's doing, it's just the composition. For example, various types of class diagrams, like association hierarchies and association diagrams. These are types of class diagrams that we want to model so that we model the domain that we are building the system for, and we have a good idea about what classes we need to write or design later. Entity relationship diagrams, which you would have seen in database design. Before building a database, we need to design it and need to analyze what sort of data entities this database needs to keep or model. Software architecture as well. We'll see an example of software architecture today, but software architecture will also show you the major components in the software. And if we say software systems architecture, then again, what needs to be around the software to enable it to function properly. So again, these are all structural models. They show you the composition. You try to show the composition of the system to yourself as well as to your colleagues and your stakeholders. Finally, we have the behavioral type of models. And the behavior is about how the system dynamically responds to external data or events. How does it behave over time? What sort of happens? What sort of changes or phases it goes through as it lives on. So this is very much an execution kind of viewpoint, so like in the system in action, as it were. One very important aspect of modeling is that because you will end up having a number of models for the same artifact, so for the same software system, it's very likely, it's almost inevitable, that you would model the same software system from a number of these viewpoints. Not necessarily all of them, but you'll have to have a number of these. When you have a number of these models, because you are describing essentially the same software system, you need to make sure that they are consistent. They are not contradictory. They make sense when put together. Yeah, you're not going to put them as and fit them together, but you're going to have to compare aspects. So take one example. If you have an interaction diagram in terms of something like sequence diagrams, a sequence diagram would describe how objects would interact. Now, these objects would have to have parent classes, won't they? So the classes from which these objects are instances will have to have shown up, would have to have been included in the class model. So this is one example of cross-checking models together to make sure that they are consistent. Right, let's look at structural models here. One famous structural model which you would have seen before is the generalization model, class generalization or class hierarchy model. And you know, you would have seen something like that before. So for example, we have a doctor and we have types of doctors, a hospital doctor and general practitioner. So the convention is that we put the superclass or the general class at the top and the subclasses or the more specialized classes that inherit from the superclass beneath it. And this sort of triangle is the UML notation to indicate that there's an inheritance relationship between the superclass and the subclasses. And again, when we have a hospital doctor, we still have types of hospital doctors like consultant and team doctor. Yeah, again, that means that these two subclasses inherit. What do they inherit? They inherit various characteristics of the hospital doctor, like attributes and methods and behaviors. Going one level down, a team doctor here has subtypes or subclasses. Yeah, the subclass subtypes are not exactly identical, but they're very similar. So the subclasses of team doctor include a trainee doctor and a qualified doctor. Now again, both trainee doctor and qualified doctor would inherit the characteristics of the parent class, which is the team doctor. Yeah. Now, this is one of the strong arguments for following this type of modeling or applying it, is that they said it comes naturally to us because we normally in everyday life, we associate things that are similar together in the same class. We say they belong to the same class, you know, like kids, when they classify a dog, a cat, a donkey, and a lizard as belonging to class animal. This is simplifies things for them because they can then think of all animals having common characteristics, and this would be like common to all subclasses or members of that class. So this has a certain amount of cognitive economy. So instead of us people having to learn the detailed characteristics of every entity that we experience or deal with, we simply place these entities in more general classes, yeah, super classes that combine all the general characteristics together in the superclass. So this makes life easier in a way. Now, this also helps us to infer that different members of these classes share some common characteristics amongst them. Yeah, they all, for example, behave similarly or similar in some way. Like if we say both squirrels and rats are rodents, so all the characteristics of rodents are shared by squirrels and rats and mice and what have you. Now, it is often useful to examine the classes in the system to see if there's a scope for generalization. So that's how we build the model of classes. We see if there are similarities between a number of classes that help us sort of abstract the general parts, collect the general features together at a higher level class, and have a generalization hierarchy. So the general thing is at the top and the more specialized thing at the bottom. Specialized in the sense the specialized class has more features, has more characteristics, has more attributes, variables, methods, operations, behaviors, what have you, it doesn't matter. But please understand that there's this sort of cascading model of features and characteristics coming from the top to whatever is beneath it and connected to it with an inheritance relationship. And now if we do that, then we don't need to look at all the classes in the system to see if they are affected by change. So basically, we look at the classes with the common features, and we know that all the subclasses of that would be affected by change at the superclass, but not everything else in the system. That's important. It makes things easier. I can think of the practical consequence of this is that when you need to maintain a system and change the behavior of the features of a class. Then if you've collected all the similar classes together and abstracted them under a superclass, then you can mainly affect this change or affect that change in only one point and not go around all the classes to implement them. So that's important, makes your life easier. And that was one of the main sort of justifications for applying object-oriented and class-oriented modeling, is that you will be able to reuse your code and your descriptions at the higher class and the lower classes. So the reuse objective was really important at the time. It was strong justification for doing this kind of modeling. So a bit of like historical justification there for you. Obviously, it works in this way, but not maybe as everybody imagined at the time. Now, an object-oriented language like Java, generalization is implemented using just normal class inheritance mechanisms, which you would have experimented and used in a language like C++, where you specify a class, a new class to belong to another class that you've already defined. That means that the new class would inherit the general characteristics, all the characteristics of the superclass, yeah, using class inheritance. Obviously, when we create a generalization hierarchy, the attributes and operations associated with the higher level class would be also associated with the lower level class in the sort of inheritance relationship, as I said. Now, often we need to add more specific attributes, some additional attributes and operations to the lower level classes, because, you know, okay, I have at the top there a doctor, and beneath it there's a hospital doctor and like a clinic doctor. But in the clinic doctor, I will need to give maybe something like a GP license or an address, clinic practice address, or distance to travel, something specific to that particular subclass. So we can always add extra attributes and operations in addition to the attributes that the subclass has inherited from the superclass. Yeah, so superclass that gives its features and attributes to the lower level class. So the lower level class inherits the attributes of the superclass, and then I can add more features and attributes at the lower level. That's why when we look at the hierarchy like this, we can say that if we go down the hierarchy, we are getting more specialized. So going down is a specialization direction, because I'm adding more specific or specialized attributes and operations, and going up we're generalizing. So going up is generalization because we're losing some of the at lower level attributes and operations. We're getting more abstract, yeah, we're getting more general level. So again, I hope you can see the sort of economy modeling that this sort of modeling achieves when we do that, when we apply the software development and use this mechanism for modeling the domain of operations, the domain that the software is meant to reflect or behave like. Now we add a bit more detail, so inch a bit closer to design by adding attributes or variables to each class type, and we add operations as well. You notice here at the subclass level, you don't have to repeat the common attributes because they're already in the higher level, the superclass. So this really means that each of these subclasses, hospital doctor and general practitioner, will inherit the common attributes at the top there given to doctor, like name, phone, and email, as well as the operations as well. Yeah, so they inherit everything. Now, if one of the methods or operations work differently at the lower level class, as you would have seen in your C++ programming, I simply redefine that operation, and then only the new definition is operative in the lower level class, because this is the scope of its application. Right. An aggregation model shows how classes that are collections are composed by the class. Sometimes I put some class together to get a higher level of class. This is not inheritance. We're not talking inheritance here. We're talking like collecting things together, like combining things together, composing things together. Now, essentially in aggregation models, you can define a belongs to relationship and a part of relationship, as you might have seen in semantic data models. Yeah, if you haven't seen semantic data models, don't worry about it. It suffices to say that we have two types of aggregation: belonging to something, but you don't necessarily exclusively belong to that top level class, and part of, where the relationship has to be more exclusive, like it can be only part of one object at a time. Let's look at a couple of examples. Now, here's the aggregation association. This is not inheritance again. This is just to say that the patient record is an aggregation of the data on patient and the consultation. Yeah? Or it associates patients and consultation. So this is like an aggregation thing. Let's look at another example. If we have a university or teaching class, we can say that this class is in an aggregation relationship with both lecturer or professor and student. Yeah. So notice something here, that the semantics of the domain, i.e. the meaning of the domain, if we may ask questions of our clients and users and understand the domain better, they would mostly or most likely tell us that a lecturer can actually belong to more than one class at any one time. So the relationship is not exclusive. It's not like monogamous there. Same thing for a student. A student can participate in more than one class. So the aggregation is just putting things that belong together. Okay? So here we say both a lecturer and a student can belong to more than one class. Sometimes you don't have that. You have to make an exclusive relationship. Let's look at how we model that. But let me just point out how hollow this diamond is. So this diamond is the symbol or the notation used to indicate an aggregation in UML class diagrams. Now, if you want to say the relationship is exclusive, so the classes at the bottom here cannot belong to more than one of the classes on the other side at the top of the relationship, then it's a composition aggregation. It's a part of a relationship, which is a stronger form of aggregation. Why is it stronger? Because an engine cannot be in more than one vehicle at any one time. It's composition. It's like physical composition. It cannot be in more than one vehicle at any one time. Same thing for body panels. So like the boot or the door panels cannot be in more than one vehicle at any one time. And again, we have something about multiplicity here to sort of say you can have at least one to many body panels present in any one vehicle. And often we need to name the relationship and indicate multiplicity or cardinality. That's the number of instances of the classes that can participate in the relationship. So let's look at this example. We're saying here that a bank can have 0 or many customers, or 0 to many customers. Yeah? So basically, this indicates that the business rules indicate that we can actually have a bank with 0 customers. It is still a bank. And maybe in another system, another domain, under different regulations, the rule might be, a bank cannot exist unless they have one single customer. It's like saying in university, a class cannot exist unless there's at least one student registered. Or we can say, the minimum number of students in a class is 15, so that will be the minimum number of students participating in a class relationship. Okay, so here we're indicating the multiplicity or the cardinality relationships or constraints that has to apply to this kind of relationship. Look at the remainder of this hierarchy or this association diagram, where we say a customer can have 1 or more accounts. So it's got more business constraints, your business rules that say I cannot have a bank customer unless he or she has at least 1 account in this bank. Yeah, and that's indicated because we have the multiplicity constraint running from 1 to many. Okay, again, we see like a lot of rich and powerful symbols and types of notation that help us model the nature of the domain, how it works, reflect its business rules and its composition, which is really important. Sometimes we can have sort of like a flexible relationship where a class can have a relationship with itself, or can have an association with itself, but named differently. So staff member can be manager of other staff members. So staff members can be manager of 0 maybe members or many. Also, we can have a staff member being a managee or managed by a staff member of the same time. So this is like what can associate a class with itself. So self-association with the roles that are different depending on the direction I'm reading. The role can be either a manager or a managee, as you can see here. Right. So I mean, just think of this as a particular perspective on the domain that you're trying to model to develop software for. Yeah, it's a structural perspective. Okay. Now let's go to behavioral models. Now, behavioral models aim to describe how should the software behave under different conditions. Describing behavior this time. Yeah, not the structure, not the static structure. This is more like a dynamic perspective, looking at the software in action, or describing what it should be like in action. How does it respond and how does it behave? So the behavioral models are models of dynamic behavior. Yeah, it's view a system as it is executing or as it should be executing. So they show what happens or what is supposed to happen when a system responds to external stimulus like an event from its environment. So it's behavior. Now we can think of these stimuli is the plural of stimulus, as being of 2 types, either data, so some data arrives that has to be processed by the system, or events, some events like an indication, a signal of something. Obviously, this can be indicated by data as well, but event would be important in terms of its timing, etc. But events don't always have to have data associated with them. Yeah. So the response or the stimuli can be either data or event time. Sometimes it's even simply just time passing. Yeah, which is some people treat as just a kind of an event as well. Okay. If we're doing behavioral modeling, looking at data, we can develop a behavioral model that is data-driven. a behavioral model that models behavior, but it's data-driven. It's directed by data. It depends on data. Therefore, and the model needs to show the data, what data is coming, in what directions, etc. Many business systems are data processing systems that are primarily driven by data, like a customer issues an order, gives an order, sends an order. Yeah, a bank account, bank customer withdraws or deposits money. So these are controlled by the data input to the system. The content of the data input is what triggers behavior. Yeah. So relatively, there's little external event processing. Well, this can be a bit philosophical. They can say, okay, well, the order arriving to the system is an event. Well, let's not get too philosophical about this. Data-driven models show the sequence of actions involved in processing. So what happens once I receive an order from a customer? What happens once a customer deposits some money or withdraws some money? Yeah. So we show what happens and what is involved in processing input data and generating an associated output. Obviously, you get an input, you do something with it, you generate some kind of response, yeah, some kind of output. So what are the links? What is the sequence of steps and actions that happens between the input arriving and an output is generated? Now, they're particularly useful when you're analyzing the requirements because they can be used to show end-to-end processing. You can actually show the logic of how certain inputs are converted or turned to certain outputs, or how certain outputs are generated on the base of inputs that have been arriving to the system. So this is particularly useful if you're looking at a kind of transactional system or a business-oriented system. Even for control systems, actually, we could do that. Now, this is just the case study that we're going to use for some of the models that we look at here, which is an insulin pump control system. Now, the insulin pump is a device called for patients with diabetes. Its function is to collect data from a blood sugar sensor or blood glucose sensor, and it calculates the rate at which the insulin needs to be injected. Yeah, if it's going to up too fast or is dropping too fast again, this will affect the amount or the dose of insulin that needs to be injected into the patient. Now, the calculation of the insulin is based on the rate of change of blood sugar levels as collected and calculated from the sensor. Now, the system sends signals to a micropump to deliver the correct amount of insulin to the patient. Obviously, this might be a physically small system, but it's actually safety critical. Safety critical because the wrong calculation could actually lead to very serious harm to the patient. So low blood sugars can lead to brain malfunctioning, coma, possibly death. High blood sugar levels can lead to damage of some of your vital organs like eyes and kidneys. So it needs to be done properly, correctly. Now let's look at this is actually a structural model, but I think it is worth just putting here with the insulin pump example. This shows the main components of the software. Yeah, so this is the software architecture, the main components, the software comprising the software architecture, the sort of coarse-grained components of the system. So the insulin pump has a pump, it has a controller for the pump, it has a clock, it has an alarm that can be triggered, it has one or more displays, it has a number of sensors, and it has a needle assembly that would actually be injecting the insulin into the patient. And again, around that, we need an insulin reservoir, the insulin that is actually going to be injected, as well as power supply to enable everything here to work. Yeah, so this is a generic, high-level description of the software system here. I encourage you to always develop something like that for your software system. Have an architecture that describes the general composition of the system at a high level of abstraction. Now, let's model this. Now, if you remember, this section is about behavioral models, and this is how the thing looks from the top, from a high level architectural point of view. Now, if you look at how it's going to be actually done, so here's an activity model. So it's a process it's a process-oriented model of the functionality of the software. So this is basically a description of what the software needs to do. So and here, three symbols are used: a rectangle to represent objects or data flowing between, going from one activity to the other, and the rounded triangles are, the rounded rectangles are the actual activities. So here's an object going to this activity, get sensor data, which obviously will be translated into some kind of coordinate system eventually, and this activity passes sensor data onto another part of the software, which would compute sugar levels, and the sugar levels would be used to calculate insulin delivery, and so on and so forth. You can follow that as a process, a sequence of processing steps, a sequence of action that ultimately generate the actual measure that the control pump needs to push the insulin into the patient. I showed you something very similar like this earlier on, which I call the data flow diagram. The data flow diagram is very similar to this, except that we don't show the data as blobs like that or rectangles like that. Simply write down the data on the arrows. Yeah, so the arrows represent the data flows, and these would be the processes or activities that have to be carried out. Yeah, so this is a data flow model. Yeah, it shows process. So we were depicting or modeling the process via a data flow model. We're showing the process by using the syntax and semantics of a data flow model, but we are modeling process here. Yeah, so don't be confused when people say, "Oh, this is a data flow model," or "This is a process model." Yeah, it is a process model, but in the language of data flow, because you could also show the process via a sequence diagram. Yeah, we could show the process via depicting or modeling the sequence of interactions amongst the objects in the system. Again, it would be like to describe a process model. Now, one question I want to think about is can we regard one particular type of model to be of both types? Think about that for a minute. There's an error in the 9th edition of this book. If you've been using it, it's just as good as the 10th, but there's just some minor errors that I corrected here. If you still use that edition, that's okay, but you just make sure you fix these issues in your book by changing some of the diagram numbers. Okay. An event-driven modeling of the process. So we've talked about data-oriented or data-driven models of process. We can also do this by event-driven modeling. Why is that? Why we need that? We need that in real-time systems, because in real-time systems, these are systems that need to provide an immediate response. They react very quickly, yeah, with very hard timing constraints. In the sense that if the timing constraints are not observed or are not adhered to, something very serious is going to happen. Yeah. So real-time systems, as in like a process control, a factory, like some process that is being monitored or controlled by software, a nuclear reactor, a chemical process. These are all examples of real-time systems. A fly-by-wire system, a system that would maintain the trajectory of a spaceship or a rocket or something like that. Again, these are all types of real-time systems. For example, a landline telephone switching system responds to events like the receiver being taken off the hook by generating a dial tone. So as soon as the receiver is taken off the hook, a dialing tone would be generated. So this is a real-time system. Now, event-driven modeling shows how a system responds to external as well as internal events. Yeah, that's why I call it event-driven. It receives an event, which could be from the outside, completely outside the software, or an event that has been generated by another component of the software. So it's an internal event, like, for example, a printer running out of paper, or reaching the end of the file. Yeah, so this would be like types of events that the system needs to generate an appropriate response to. Now, in the model that we see, which discuss or model state, uh, uh, the assumption is that the system has a finite number of states and that the events may cause transitions from one state to another. Yeah, so this is essentially what event-driven model is. So we have events that are driving the changes in states of these systems, and the states are finite. I can predetermine what these states are going to be. There are no surprises. Yeah, so we can do that. We can do that. I'll show you some of the models. One of the specialist methodologies for modeling real-time systems is called Mascot. Yeah, I mentioned that in the previous slide, and this particular methodology has been used in a number of defense systems and weapon systems in the British Army, etc. And it's very good. This method has been developed to model explicitly, to show you the important things that we need to model in real-time systems, namely things like mutual exclusion, timing constraints, and cross-stimulation of processes. I'll repeat these: timing events or time-related events, cross-stimulation are like one process triggers another process, cross-stimulates another process, and preventing undesirable deadlocks or mutual exclusion. That like no two processes of a particular type would be active simultaneously. Otherwise, this would lead to errors. Now, we've got some specialized versions of UML that are aimed at real-time systems by adding extra like primitives and extra modeling primitives that would explicitly show aspects that we're interested in. So, for example, UML has a profile. A profile is like specialized set of modeling elements called MARTE, which stands for Modeling and Analysis of Real-Time and Embedded Systems, that has more primitives, more modeling notations to model explicitly, specify on the diagram or on the model what things that we need to manage or control or reason about on the model before actually going to build the software. A profile in UML provides a generic extension mechanism for customizing UML models for particular domain and platforms. Yeah, so you can actually add a little bit that says, okay, for example, for a device driver, I would have a specific printer driver. Yeah, and I will label that as being specific to this particular function. So that's the notion of a profile. Two of the things that we need to explicitly model in real-time and embedded systems is the quality of service. For example, like we need to generate a response by a certain time. I know I said before that this would be an unfunctional requirement, but sometimes we need to put that explicitly on the model so that the designers know how hard the quality of service constraints are, and therefore they can respond to that appropriately. And we can associate these with classes because they need to respond in a certain way. Also, we need to add information about resource usage constraints, for example, like how much time and how much storage or any other resource that might be needed for processing, as well as any constraints like this is the maximum time you can use, or this is the maximum storage or memory space you can use for this particular component. So it's about enriching the models, adding more details, using standard notation that everybody understands who works in this kind of type of system to make things that need to be controlled and designed in early as explicit as possible. We don't want people to make assumptions. We don't want them to get creative with something that is critical. We don't want them to decide by themselves. If it's something that the designer can decide early on to make sure that the whole system works properly, they need to put it explicitly on the model. Okay, state machine models is a type of models that are very useful for real-time and embedded systems. because they show these aspects that we really care about when we are trying to build software for real-time and embedded systems. Yeah, this is a behavioral model. It's not obviously a structural model. It doesn't just show structure. It shows behavior, and it shows behavior over time. So it's dynamic behavior. Yeah. So this is important to know this particular type of model, what type it is, and what is it used for. The state machine models you would have seen before, and I'll show an example in a minute. Just let me show you how it looks like. This is a state transition diagram or state diagram of the microwave oven. You will see here that we have symbols for the start state and for the end state, and the rounded rectangle represents states, and the thing inside the do whatever indicates the action that needs to be taken in that state. Yeah. So while waiting, you need to display time. Yeah. While the oven is in the waiting state, it needs to display time. On the arrows here, we put the conditions or the stimuli that cause the transition from one state to another. So from the waiting state, if while the oven is displaying time, if the user selects half power, then a transition would happen from the waiting state to the half power state. If the user selects full power, this will cause a transition from the waiting state to the full power state, and so on and so forth. So the user keeps selecting various conditions and timer things, maybe levels of whatever, set a time. All these would be actions that would cause transition in the state from one state to another. For example, if the door is open after the time is being set, then the machine would not work. The door has to be closed for it to be enabled to actually to function. Yeah, and from that state, then we can press start to make it actually operate. So it's like discrete set of states, a finite set of states, and we model very explicitly how the machine or the artifact would move from one state to the other under what condition. This thing at the bottom half of the state description here is optional. You don't have to have it all the time, but sometimes it's useful to indicate what the machine should be doing while it is being in that state. All right, so let's go up again. So the state machine models model the behavior of the system in response to external and internal events. Yeah, and the events would be indicated by these sort of conditions. Yeah, someone selects power rating or sets a timer, then this would be the event that the system has to respond to. Now they show the system response to stimuli, so are often used in modeling real-time systems and embedded systems, of course. The state machines models the states as nodes, or maybe boxes or circles or whatever, and the events connecting these nodes, which obviously represent states, as arcs, just like a graph. Yeah, it's effectively a graph. When an event occurs, the system moves from one state to another. And we model that explicitly because then we translate that into interactions when we actually write the software, or behavior transitions when we actually write the software for it. Now, the name that state machine models or state transition diagram models take in UML is called state chart, which is a notation due to David Harrell, who actually developed them and called them state charts. So state charts are part of UML and are used to represent state machine models. Okay, so we've seen that. So this is the state diagram using state chart notation. Now it's very important to note what happens if, this is obviously fairly simple, it's a simplified model of a microwave oven. What if it's like a really realistic and very large one? This is a problem that happens always with models of complex systems. The model, even from just a single viewpoint or perspective, can get so large so as to become like cognitively very complex to manage. It's hard to get your head around it, hard to read and understand. So what we do is, normally there's a device or method for structuring the specification, usually in a hierarchical manner. Like, for example, if the operation state here is actually in itself composed of other substates, then we simply take that out. We keep it as it is on the diagram, but we expand it or explode it in another part of the diagram, like so. Yeah, so remember, what is this called? It's operation, and what it do is operating the oven. Okay, let's look at the details of that. So we open it up and look inside. Under operation, this is a notation of doing it. We have other substates which take it from checking the status that the machine is in good working order. There are no faulty parts that can lead to malfunctions or dangerous situation. If everything is okay, then we cook. We stay in that state until time runs out, and when it's done, we trigger an alarm. Yeah, and then we go back to the waiting state for the next instruction. If the checking results in some kind of fault, either a turntable fault or an emitter fault, that's the microwave emitter, then we generate an alarm, display something maybe, and then the machine is disabled, and we don't allow the microwave to function if it has any of these parts being faulty, because it's dangerous, obviously, because of the radiation, etc. So this is an expansion or an explosion or detailing of the higher level state that is labeled here as operation. There are further descriptions here, like, let's look at the states then. We describe the states. So the waiting is about, we just give more details, we elaborate, to explain to the reader what waiting is, what is involved in waiting. So we say here, the oven is waiting for input, the display shows the current time. What is set time? What is this state? The cooking time is set to the user's input value. Yeah, so this is what we mean by this state. We mean that the cooking time has already been set, and the display shows the cooking time selected and is updated as the time is set. Yeah. So, and let me go back to this a little bit and just remind you of this thing. I'm saying here, annotate and explain. It's not enough to just have a set of pictures and some boxes, nice boxes and arrows and circles and what have you. You need to add annotations and labels so that when people read your model, they can make sense of them. These models are not meant for the computer. We're not going to feed these diagrams into compiler, although there are some developments where you describe your programs visually and stuff like that. But these visual diagrams are not intended for machines, they're intended for human users. So they need to be understandable. It's a very important characteristic of models. They need to be understandable. So you need to add text, annotation, explain, and use meaningful names and labels for these. Meaningful as in indicating the content, making the understanding task easier, yeah? So that they're more obvious, they're more explicit. You want people to need to make fewer assumptions, as few assumptions as possible, as humanly possible. So you need to make your model as self-explanatory as you possibly can. This is good engineering and good modeling. Yeah. So when we describe the states involved in this diagram, we say what each state means. It's for the human reader to understand and make sense what each of these states imply. Same thing for the stimuli. So we put every stimulus in a table and describe what it is. Half power, what does half power mean? It means that the user has pressed the half power button, or maybe selected medium power or whatever. Yeah. What does number mean? What does this stimulus, what does it mean? It means that the user has pressed a numeric key or more than one, if you allow that. Again, door open, it's a condition, it's a stimulus, it's an indication that the door or the microwave is open, then therefore the switch is not closed, or the latch is not closed, so the machine should not operate as would be explained or modeled in this model. If the door excuse me, if the door is open, then display then the whole machine is disabled. So this is the state it's in. It would not work if you allow the microwave to work while the door is open, it's an extremely dangerous situation because the microwave energy will flow out, possibly harming people because it's very high energy. It's radiation, basically. Okay. Now, I want to move to a slightly different kind of model, which is the model that depends on formal notations in mathematics. We have two different broad categories of formal specification language. Remember I said that you need to describe requirements using some kind of language. And the visual languages that we looked at before, the various types of models, are what some people can describe as semi-formal methods or semi-formal notations, because they have reasonably defined semantics and syntax. All these diagrams that we saw earlier, you cannot just draw them however you like. There are rules and ways of drawing them correctly, but they are still a bit loose. The meanings of these diagrams and models, or the primitives used in them, is not like 100% tight. So if the systems that we're dealing with are really very safety critical and cannot afford to have errors, then we resort to more formal languages, more formal specification methods. Two broad categories. One is called algebraic, which expresses the functionality via a set of relationships between axioms, algebraic axiom and expressions. Another one is called model-based. So we think of the software system as a model comprising a number of states, and we describe the constraints that operate on these states and how the various operators would change these states. So it's a bit like the finite state machine model and the state charts, but the effects of events and the transition are described much more formally using mathematical notation. Yeah? So two broad categories that you need to know now: algebraic as well as model-based. And we can use them to either describe sequential systems whereby only one operation, one process is active at any one time, versus concurrent systems. Now, for each of these categories, we have different notations. So, for example, if you want to describe concurrent systems using algebraic notation, you have Lotus, which is an algebraic type formal language for describing concurrent systems. If you want to describe concurrent systems by using model-based notation, then you have Petri nets, which are very similar. In fact, the state transition diagrams are based on Petri nets, so they're the same type of thing. Or CSP, which is due to Tony Hoare. CSP stands for communicating sequential process. It's another formal notation that describes the system as a set of states. Yeah, so it's model-based. It's got models. Okay, but we're not gonna go into detail in that. Let me just show you one example of formal methods. This is an example of state-based specification. This is in the formal language called Z. It's state-based or state-oriented specification language, and we describe various constructs in the system as states, and we use this notation, which is called a schema. At the top left-hand side there, the name stock is the name of that schema. It's called stock. So it's like I'm describing an inventory system, and I'm describing the constraints that operate on that inventory system. So it's called stock. And in the stock, I have these variables. I have a variable called stock ID, and the domain of that stock ID, because it's a number, is the set of all natural numbers. So it can be anything. Yeah, of course, you can have more specific domain constraints on that, but just the type of that particular variable. It's all natural numbers, which will obviously exclude negatives. Yeah, because in nature there are no negatives. Yeah, you can have 0 or more. The stock level is a mapping between, or a mapping from the stock ID here that set of stock IDs to, again, the set of all natural numbers to indicate the stock level for each particular ID. So the stock level would map each stock number to the stock level, i.e. the amount you have of it. The stock name is described in letters, so it would be a mapping from the stock ID again to the sequence of bytes that actually expresses the stock name. The stock value is very similar to the stock level in terms of the mapping. It's again a mapping from the stock ID to the set of all natural numbers. So here we've described the state variables or the schema variables. What are the schema variables? What are the domains that comprise the schema variables and the mappings between those domains? So the variables are described as either a set or a functional mapping between two sets, just like in the function we've described or you studied under discrete mathematics. Now let's look at some constraints. Now at the bottom bit, we describe the constraints that operate on the schema variables. For example, that the domain of all of the stock level is exactly the same as the stock ID, which means that every stock level would be associated with a stock ID. Yeah. The other constraint says that the domain of stock name is a subset or equal to the domain of stock level, which is basically to say that you can have some stock items, you have a stock name, but without an associated stock level. So it's a new item that you intend to acquire, but still don't have a stock level for it. Yeah. So the domain of the stock name could be a subset of the domain stock level. Same thing for value. You can have a stock ID that does not have a value. So the domain of the stock value, remember the stock level is a mapping between stock ID and number. So the domain of the stock value is a subset or equal to the domain stock level. So again, this is to say all the stock IDs would have stock levels. Yeah. Some of the stock names would have stock level. Yeah. And some of the stock values would have a stock level or not. Yeah. So yeah, it's a way of being more precise about how your description within the system of a stock file or a stock entity or state would be like at any given moment in the life of the system. Moving on, I mean, I don't want to explain all of this, but just look at the general shape of it. This describes the effect of an operation called add item. Yeah. So when you add an item, you get some inputs, and the inputs are indicated by this question mark, and the result is a response. And inside this particular variable part, constraints part of the schema, you would indicate the relationship between the stock level after the operation and before the operation. So the stock level prime indicates the stock level after implementing a particular operation. So, for example, the stock level here, once you've added a new item, the new stock level, which is primed, would be equal to the old stock level in addition to a new mapping from a stock ID. Yeah, remember this stock ID is indicated by S, and it comes in as an input, so it has a question mark. So the stock ID is mapped to a stock level. So stock ID is mapped to a stock level. So this mapping is united with the earlier mapping of stock level. So the mapping or the union between the new mapping and the old set gives us a new stock level, which is after the addition of the new item and its new level. Yeah. So let's so basically, you need to read this to try and make sense of that. we call it the schema decoration. So the question mark indicates input, the shriek indicates output, and the prime is the state variable after the operation. What becomes of it after the operation? And the operation here is add item, because when we add item, we simply add this new mapping, a mapping of a stock ID to a level. So we're adding a new item to the stock that we have. So the new mapping is in addition to the old stock level, and together the union of these becomes a new stock level, and so on and so forth. But obviously, if the item being added, notice this, if the item being added is already within the domain of stock level, it has been defined before. So I already have a stock ID with this ID present in the mapping of stock level. So it's already in the domain. So I generate the response. The stock identifier already exists or is already used. We cannot add a new item and claim it's a new item if it already exists. And remember, the stock level is a mapping. According to this, the stock level is basically a mapping from stock ID to the set of natural numbers. Yeah, so it's basically a set. Yeah, and the domain of this set is exactly the same as the stock ID. So any IDs in this stock level must be exactly the same as the whole set of IDs that you've had before. Okay, I'll just skip this because I've already mentioned that. How are we doing for time? Okay. Now, this is something that I want to mention briefly. It's in the book. You might want to read more on it, but there is a type of software development called model-driven engineering. It's not really that different from what we discussed before, but there's one or two things that's worth mentioning. But in model-driven engineering, we try to concentrate or focus on models. Yeah. So this is very much in line with with this lecture so far, or this part of the course, that we deal mainly with models. So we concentrate on generating models, and we get a detailed enough models that can be translated automatically or semi-automatically with some assistance to generate actual code. So the programs that execute on hardware software platform are then generated automatically from the models. Yeah. So we keep transforming models, keep generating models, and deriving models from other models. Let me give you a very simple example. You have an analysis model, a model of requirements. You evolve that or develop it or base a design on it. Yeah, you develop a design to realize that specification model, the requirements model. So the requirements model that has this requirement specification is used to generate a design, and you keep lower the level of abstraction until you get to a point where the models can be automatically translated into actual software programs. Now, people who defend this style of development say that it raises the level of abstraction in software engineering, which means that software engineers can concentrate more on the conceptual parts and the actual problem domain, describing it and getting the requirements right, and generating a good and valid and robust design for it. I'm not sure what happened there. Right, let's share the screen again. Okay. I'm just checking whether to see whether we're actually sharing recording or not. I think we are. Yeah, we are. Okay, very good. So I hope this combines with the earlier part. Okay, so in model-driven engineering, we focus on the modeling rather than the code, and we evolve the models until we get to somewhere very close to generating the actual programs and the software. The usage of model-driven engineering, well, it's not like very popular right now, but it has some advantages. It allows systems to be considered at a high level of abstraction, which is good. And if you can actually generate code completely automatically, but this does not really happen very often, it means that it's cheaper to adapt the systems to new platforms. So you simply modify the model and you let the automatic tools generate the appropriate code for you. However, but the cons or the disadvantages of this approach is that the models for abstraction that are supported by the model may not be suitable for implementation. Yeah, so for example, you might be wanting to use COTS components. COTS stand for commercial off-the-shelf software. Commercial off the shelf. You buy things. You're not not going to generate code from your design. So this would not be, your models would not be the right abstraction for this kind of solution. Also, whatever savings you achieve from generating the code may be outweighed by the cost of developing translators for every new platform you have. Yeah, obviously that's assuming that you have to do it yourself. Maybe sometimes you get it for free, so you need to investigate that. Now, model-driven architecture was the early, the precursor of more general model-driven engineering. Model-driven engineering, model-driven architectures is a model-focused approach that uses a subset of UML to describe the system. So, model-driven engineering is the sort of the development or the later development of model-driven architecture. Yeah, but it's worth knowing about it, because I think this is really the original of it, and this is what I'd like you to consider to use, or something like that, is that you focus on generating and transforming models at a higher level of abstraction, or different levels of abstraction, from the very high level platform independent model, like I don't care about how I'm gonna implement this particular piece of software. I'm just describing the logical function, the logical content. I don't want to worry about which database, which platforms, etc. Yeah, and in theory, you could generate a working program without manual intervention or automatically. But as I said, in actual practice, this doesn't happen that often. But the advantage is if you have a model that's independent from platforms, when you get a new platform, you can more easily or with less effort translate that model to the new platform. You don't have to reconceptualize the whole thing again. So it's the idea of doing your design in stages, yeah, or according to levels of abstraction that are distinct or decoupled from each other. So here's the types of models that are generated when doing model-driven architectures. First, you have a computation-independent model, CIM, which focuses mainly on the domain models and functionality required. Yeah, we don't even assume that we're going to compute anything. Then we develop a platform-independent model. So this has the logical function and the design of how this is going to be implemented, but we don't worry about which platform, like which database, which communication channels, etc. But once you get very close to the platform, then you start to translate the platform-independent model to the platform-specific model and do all the necessary adjustments to make sure it sits properly on that platform, it executes correctly, and with appropriate optimizations that you might need to implement. So let me just read these two for you. A platform-independent model models the operation of the system without reference to its implementation. The platform-independent model is usually described using UML models that show the static system structure and how it responds to external and internal events. So it's very much like the diagrams, the UML diagrams we've been discussing so far. Now, once we get close to the platform, we produce platform-specific models, and these are transformations of the earlier model, that is the platform-independent, with separate platform-specific models for each application platform. So you could deploy that onto different platforms, for example, when your hardware arrives, or if you have different clients with different platforms that you might want to generate specific models for the particular hardware kit. Yeah, but obviously in principle, you may have layers, different layers of platform-specific models, with each layer adding some platform-specific details like printers, communication channels. Okay, one is Ethernet, one is mobile-based wireless communication, whatever. We need to translate our software to implementation that suit these specific platforms. But the idea is to keep them separate. Do not hardwire assumptions about the platform into your design model. That's the key message of this, really. We don't want to build in elements or components that are specific to technologies or platform into our design, for the very simple reason that if the platform changes, we will have to modify our design and mess with it and maybe, commit errors into it, which we don't want to do. So keep them separate. If you have to specialize your design into a new platform, then you can develop it from that point on, like from the design model. And you don't have to redo the design. You just translate the design model to a new platform. I think this diagram will help more here. So initially, we have a computation-independent model via some kind of translator, and with human assistance, we take it to platform-independent model. And here we have domain-specific guidance, obviously, because we don't want to flout or contravene any of the domain constraints, which ideally should be present in the computation-dependent model anyway. So this might not be needed, but sometimes we do need them. Okay, we take the platform-independent model, and we can translate that into a platform-specific model. And here we need some input that indicates what are the platform-specific patterns and rules, information about the platform-specific model, and again, so that we translate the platform-independent model to platform-specific model. So this transition is not automatic, or is not like mechanical, as people originally hoped for. And finally, we take the platform-independent model that we want to evolve to an executable code, and again, we need some information about the language-specific patterns and constraints. So we need a little bit of assistance here to these transformations. They're not going to be like totally automatic. Yeah, this is very useful because sometimes we need this kind of pattern, because the platform-independent model that is independent of the execution platform, we might want to evolve for different target environments. So one time we can evolve the design to be implemented as Java programs, and sometimes we want to evolve it to be implemented as C# programs. Now, we don't want to hardwire any of our knowledge or assumptions or specifics of either of these platforms into our design. That's why we have a platform-independent model. Let's go back up again. So once we have the platform-independent model, the translation step is only in here, and we don't have to start from the earlier domain model and the requirements. So we don't make assumptions in the requirements model about what platform is going to execute this. Yeah. Okay. So the platform-independent model is evolved into models that are specific to the implementation. Yeah, which is what we called here a platform-specific model. So the platform here is Java. So we have this translation step, taking the Java J2 Enterprise Beans, obviously the Java-specific model, to take it to a Java code generator, which would ultimately generate the program. Yeah. So again, it's about evolving the model gradually to get to a specific implementation platform without having to build assumptions about the specific implementation platform into our area design model, which is really important for the flexibility and modifiability of your system. Okay, agile methods and model-driven architectures. Now, the developers of model-driven architectures claim that it's intended to support an iterative approach to development, and so can be used within agile methods. But the notion of doing extensive upfront modeling is against the spirit of agile development and the fundamental ideas in the Agile Manifesto with its various principles that we discussed before. Okay, so if the transformation can be completely automated and a complete program generated from a platform-independent model, then in principle, MDA could be used, model-driven architectures could be used in agile development. But obviously, this is not terribly practical that it happens completely in a completely automated way, because we will not have to have any coding. We just translate the design into code. Right, I think we're running out of time, so I'll just have to leave you with this to read up about. I mean, it's close to the concept of model-driven architectures, that sometimes there is a subset of UML2 called executable UML, and some people have been banking on that, achieving completely automated transformation. This happens in a very small set of domains, yeah, because you need to do some work to translate your models into code. You need to do lots of adjustments most of the time. Only in like highly regularized, highly standardized platforms you can do this. For example, like dealing with print drivers, for example, or printer drivers. Okay. Here are some features of executable UML. I'll leave you to read that up. There's a link in the book that you might want to follow to know more about executable UML if you're interested. This is just for the sake of knowing that it exists. It's not like a core part of this component of the course. Okay, so what are our key points? Behavioral models are used to describe the dynamic behavior of an executing system, and this behavior can be modeled from the perspective of the data processed by the system. So we do a behavioral model that is based on data-driven, or event-driven. We can have an event-driven model. So we describe the behavior via an event model that shows you the stimuli and the responses from the system, either to external or internal events. Activity diagrams may be used to model the processing of data, where each activity represents a process step. Yeah, so activity diagrams can also be thought of as process type models. They show process by showing the activity and the chains of activity and the sequences between them. Model-driven engineering is an approach to software development where the system is represented as a set of models that are gradually transformed and evolved into executable code. That's it from me. I hope you found that useful. I'll see you in the class. Thank you very much.